Welcome to Grade 11 Artificial Intelligence. In this module, we go beyond simply labeling a picture. We'll learn how machines find objects and draw boxes around them, outline them pixel by pixel, and even generate new images. We'll also see how to grow data, how to measure success, and how to run all this on a small device far from a data center. Here is our plan for the lesson. We'll start by moving beyond classification, then compare two ways to detect objects, YOLO and faster RCNN. We'll meet segmentation, image generation, and vision transformers, and learn how data augmentation makes models stronger. Then we'll measure quality with intersection over union and mean average precision, and finish by deploying a model on a small edge device. A basic vision model does classification. It answers what is in this image with a single label. But real tasks ask for more. Object detection answers what and where by drawing a box around each object it finds. Segmentation goes finer still, labeling every single pixel so we get the exact shape, not just a box. And generation flips the problem around. Instead of reading an image, the model creates a brand new one. Each task asks more of the model than the one before it. Let's start with the most widely used of these, detection. Object detection draws a box called a bounding box around each object and labels it. There are two main styles. YOLO, which stands for you only look once, is a one-stage detector. It looks at the whole image a single time and predicts all the boxes at once, which makes it very fast and ideal for real-time use. Faster RCNN is a two-stage detector. First, it proposes regions that might contain an object. Then it classifies and refines each one. This extra stage often makes it more accurate, but it runs more slowly. The choice is a familiar trade-off: speed against accuracy, decided by what the application needs. Three more ideas extend what vision models can do. First, segmentation labels every pixel, so instead of a rough box, we get the exact outline of an object. This matters when shape is the point, such as measuring a tumor or a leaf. Second, generative models, like generative adversarial networks and diffusion models, create entirely new images rather than reading existing ones. Third, the vision transformer brings the idea from our last module into vision. It cuts the image into small patches, treats each patch like a word, and then applies self-attention so every patch can attend to every other. The paper's title says it well: an image is worth 16 by 16 words. Labeled images are expensive to collect, so we stretch the data we have. Data augmentation makes many varied training examples from a single labeled photo. We can flip the image, rotate it, or crop it. We can change the brightness, shift the colors, or add a slight blur. Crucially, the label does not change. A flipped photo of a cow is still a cow. By seeing these variations, the model learns to ignore changes that do not matter, like lighting or angle. The result is less overfitting and better generalization to new photos, which connects straight back to the bias and variance ideas from Module 1. Once a model is trained, how do we judge it? How do we measure whether a detected box is any good? We compare the predicted box with the true box using intersection over union. The intersection is the area where the two boxes overlap, shaded here. The union is the total area the two boxes cover together. Intersection over union is simply the overlap divided by the union. A perfect match gives 1, no overlap gives 0. We usually count a detection as correct if this value is at least a threshold, often 1/2. To score a whole detector across all objects and classes, we use mean average precision, which averages how precise the model is across classes and across several thresholds. Higher mean average precision means a better detector. Often we cannot send every image to a powerful server. We want the model to run on the spot on the device itself, a phone, a camera, or a small sensor in a field. This is edge deployment. To fit a model onto a small device, we shrink it. Quantization stores each weight in fewer bits, making the model smaller and faster. Pruning removes parts that contribute little, and distillation trains a small model to copy a large one, keeping most of the skill. The benefits are real: low delay, privacy, because the image never leaves the device, and it works with no internet. The cost is tight limits on memory, power, and computing, so efficiency is everything at the edge. These methods already serve very different communities. In Rwanda, drones and ordinary phones run detection to spot crop disease early, right out in the field. In healthcare, segmentation measures organs and tumors from scans far more precisely than a box could. In the United Kingdom, roadside cameras detect and count vehicles to manage traffic in real time. In the United States, warehouse robots detect and pick the right items from a shelf. And in conservation, camera traps run detection offline on the device to recognize wildlife without any network. The same advanced methods, fitted to each setting, do all of this. Before we recap, let's clear up the common misconceptions. First, detection is not just classification, it also locates each object with a box. Second, a box is a rough region, not a precise shape. The exact shape comes from segmentation. Third, augmentation must never change what the label should be. A transformation that turns a 6 into a 9 would mislead the model. Fourth, strong accuracy on one easy class can hide weak mean average precision across all classes, so look at the whole picture. And finally, an edge model is a shrunk version of the same idea, not a different kind of model. Hold these distinctions and your understanding will stay sound. Let's gather the key ideas. Vision tasks build up from classification to detection, segmentation, and generation. YOLO detects in a single fast pass, while faster RCNN proposes then refines for more accuracy. Vision transformers treat image patches like words and apply self-attention. Augmentation adds variety while keeping labels, which fights overfitting. We measure detection with intersection over union and mean average precision. And edge deployment shrinks models to run on device. Now, let's check these ideas with 3 quick questions. Here is the first question. A self-driving car must detect pedestrians in real time. Which detector style fits best? A one-stage detector like YOLO. It predicts all the boxes in a single pass, which makes it fast enough for real-time use, where every fraction of a second counts. Question 2. A predicted box and the true box overlap in about 30% of their combined area. What is the intersection over union, roughly? Intersection over union is the overlap divided by the union, so it is about 0.3. Since that is below a common threshold of 1/2, this detection would usually be counted as a miss. Last question, and it ties the module together. You must run crop disease detection on a phone in a field with no internet. What 2 steps make this practical? First, shrink the model using quantization or distillation so it fits and runs fast on a phone. Second, deploy it on the edge, on the device itself, so it works with no network connection at all. Excellent work. You now understand the progression from classification to detection, segmentation, and generation. You can weigh YOLO against faster RCNN, explain augmentation, and measure a detector with intersection over union and mean average precision, and you know how to shrink a model to run at the edge. In the next module, we turn to agents that learn by doing with deep reinforcement learning. I'll see you there.